We got a
All
moment.
right, well, I see head shaking the other way, so. What I'll do is this, give me the dates, I'll put them up, we're gonna do, this is it, all right? And I change the vote, no more. This is the final, right? There's not gonna be a recount. Matter of fact, why don't you help me on this one, and you, count hands. That way there'll be no question. All right, give me a date first, and we'll vote.
October 15th.
October, is that a Wednesday?
Friday.
Friday. All right. I said already, Friday tests usually the worst in terms of results, but don't worry, I don't care. I'm just saying this because of past experience. Another day,
I will take the unpopular Wednesday, October 13th.
oh. All right, any other dates? We're gonna have a run up, top two. Any other dates? These are it? This is fantastic. Usually I get arguments about the dates. All right, so, one hand, just one hand, you two help me. All right, if you want it, on Wednesday, October 13th, one hand up, one hand. 1, 2, 3, 4. I'm yours up or not?
No. I'm still thinking what you have candy.
I'll bring you something.
If you want it Friday, one hand.
All right.
All right, I'm not even gonna bother. What changed your mind? You.
Right.
So brides work. Okay, I'm not gonna ask any more about that, but anyway, whatever you did worked.
Candy speech.
Now I gotta tell you, see, you're all double E's, right? But I got a class I teach IEs and E, or MEs, and man, you wanna hear squabbling. Oh. Oh, this is basically painless doing it here. Okay, class, I'm gonna go through the dipole, and these are long dipoles. I'm gonna get to what the essence is, what's important. I put some of these notes up here. Before I do, does anybody have any questions about any of the homework? Yes?
Can we go over, number 20?
Can you give me the specifics, please?
Yeah, so it was given a Z polarized was halfway dipole.
Okay, hold on. This is lambda over 2 dipole. Okay, is the lambda. Go ahead.
At the origin and a driving current, I of T,
Oh, okay. Equals, go ahead.
is 10 cosine 2 pi times 10 to the 9.
T,
Yes, sir.
and that's amps. Okay, go ahead.
Find the instantaneous electric and magnetic fields. At a point,
What?
sorry.
Go ahead.
At a point, 2 kilometers distant and angle theta is 60 degrees.
All right, I'll get to this. This answers questions, by the way, this problem. So this is theta equals 60 degrees. R is 2 kilometers. And what they want is this, and H, as functions of time. Now, I'm going to develop this. I'm going to go through the mathematical reasons why this is true, all right, in a second. But I'm just going to tell you the result, because this is the thing everybody wants. If you have an arbitrarily long dipole, please listen to me, for any length. If I have a dipole any length at all, we're going to assume it's centered at the origin and in the z direction. And I have an angle with respect to the orientation of the antenna. This is important. This angle is measured from the axis of the antenna out to a distance r. Then the electric fields will always be in what we call the theta direction. If you come out a distance r away, they'll be in this direction. They'll be in the plane of the board. Y'all follow me? And they'll be perpendicular to the r vector. Now that E field, write this down. In Dr. Whitmer's book, he kind of doesn't do this. He gives you the H field, then he gives you the power density. But the E field's what you want. I'm just leveling. This E field, and this is going to be for a dipole, L greater than lambda over 10. So these are long dipoles. But it doesn't matter how long they are, as long as they're center driven, so it's gap driven and has a current I on it. Some I naught magnitude will be at the center. Then the electric field from this arbitrarily long antenna will be equal to write this down, J60 over R times I naught. Now that's just the magnitude of the current right here. Right? I naught is the magnitude of the driving current. Y'all follow me on this, class? We know that the current will be a function of Z, but the actual current right here at the origin where it's being driven by the gap voltage, that's the I naught you want. Then it's going to be times e to the minus j beta r. That's a phase term. It has to do with the phase change in the waveform from the origin. I'll spend more time on that later. Then there's going to be a function form. All right, write this down. The function will be cosine of beta L over 2 times cosine of theta minus the cosine of beta L over 2 all over the sine of theta. This is part of today's lecture, by the way. And it'll be in the A theta direction. Now that's the E field for any length dipole. Now hear me. This, in Whitmer's book, he doesn't bring this out. I'm trying to really show you, doesn't matter how long it is, that's the E field. You see this function of angle here? What I like to do is call that small f. I just like to do it small f of theta, and I call that this is the angular function. It's cosine of beta L over 2 cosine of theta minus cosine of beta L over 2 over the sine of theta. I call that f of theta, and then I say E in general. Let me put it here. E can be written as simply J60 times I naught e to the minus j beta r over r, and then it's times small f of theta, and it would be in the A theta direction. Y'all follow me? I do this for a reason with a small f of theta, and you'll see this. Now, if you wanted the power density in the far field, how would you get it? Not you guys up front, somebody in the back. How do I get the far field power density? Anybody? This should be something you know. Far field. What is the power density? Always. It's proportional to E squared, is it not, class? Magnitude of E squared, then you would divide by 2a to naught, right? Y'all with me? It would be in the AR direction. How many know that? If you didn't answer, don't worry about it, but how many know that? I mean, if you don't, you got to know this stuff. This is something. So for the far field, the power density, this is average power density, all right? And in our case, it will be a function of r and theta, is equal to 1/2 magnitude of the E field squared over eta. It will be in the AR direction. It's always going radially outward, and units of this are watts per meter squared. Now, for an arbitrarily long antenna, what this will come down to, y'all see how what I can do is, well, when I take a look at this, I have an angular function right here, right? If I take this in squared, I get 60 squared I naught squared, right? Since it's magnitude, that e to the j term zaps out, right? And it's going to be over r squared, right? Then it's over a, correct? Well, a way to write this down succinctly, and it's in his book, he has P av simply as 15 I naught squared, you could prove this, over pi r squared, and then it's going to be times what Whitworth calls f of theta, and that f of theta is my f, small f of theta squared. Y'all see how this right here is the angular variation. When you get power density, you got to square the E field, right? So this becomes squared. Y'all see that? Now this is the form Whitworth's book has for P average. And this was in the AR direction. It's in watts per meter squared. But the reason I did this with a small f of theta is this is the actual angular function that the E field varies by. Do y'all follow me? If you want to know where this is in the book, I may not have a page number, but it's in the section of arbitrarily long dipoles, and I got a whole bunch of notes. I don't have a page number for this, but I know it's in there, all right? You can check that. And that formula right here is the one that's in Whitmer's book, right here. Now, this is for an arbitrarily long dipole. I'll prove that in a second. But since you asked this question, it's all applications now. Now, when we have a dipole that's L over 2, y'all with me? Listen to me carefully. They gave us the current, didn't they? They were nice. So if it is a lambda over 2 dipole, I'm going to get the E field from this equation. Please listen to me. Well, I look at the term beta L over 2 because it appears here and here. Y'all see that? Now the length of the antenna is exactly lambda over 2. Beta is 2 pi over lambda. Do y'all agree with that? That's what beta is by definition, right? It's 2 pi over lambda because beta lambda would be 2 pi. That's the definition of wavelength. Then it's times L, which is lambda over 2, and it's divided by 1/2. Now I think y'all can see that this is going to be pi over 2 radians. Do y'all see that? Class? I'm just showing you, I want the coefficient established, that beta L over 2 would be pi over 2, correct? Can y'all see why I did that if you look at this equation? Well, what's the cosine of pi over 2? That's the cosine of 90 degrees. What is that? 0. Goes away, doesn't it? So when I come over here and write the E field, it just becomes J times I naught, and that's just the magnitude of the feed current, times E to the minus J beta R over R, right? And then it's times that F of theta. Well, since this term went away, it's just this term right here, and beta L over 2 is just pi over 2, so then it becomes times cosine of pi over 2 cosine theta over sine of theta. And here would be in the A theta direction. Now that would be the phasor form of the E field. Right? Y'all with me on that? That's a phasor form. I mean, there is no cosine of omega t here. Y'all follow me in that class? If you want the time domain form, here's how easy it is. I could write a formal mathematical equation. You don't need to. You see this right here? And this? The E field in the time domain. Technically, it's what? It's the real part of E to the J omega t times E vector phasor, which would be this. This is a vector phasor. You don't need to do that. I'll just show you how easy it is. The only thing that's going to happen out of here, I'll get rid of that J, right? I'm going to go ahead and I'm going to do a few things. But first, I'm going to go ahead and get the magnitude. This would be I naught, which is going to be the I naught of the current, whatever it is, 10 over R, right there. Then it's going to be times cosine of pi over 2 cosine of theta over the sine theta. Now we know he gave us a 60-degree angle. I'm not going to mess with it. I'm just putting the form in there, all right? 60 degrees tells me cosine is 60 degrees is a half. Pi over 2 times a half is pi over 4. The cosine of pi over 4 is 1 over square root of 2, right? The sine of 60 degrees right there is what? Square root of 3 over 2? Y'all follow? You can do the math on that one. That's not hard, right? Now here's the part that does get really interesting, but I don't ever worry about the phase term. For the instantaneous form, you see that J? J can be represented as what? As E to the J pi over 2. Do you agree with that? So I can go here, and since that's a minus, it would be minus pi over 2. Now, I don't ever test on this level of detail. I'm just telling you how it would appear. I would incorporate the phase there. Y'all follow me? If it's a j out in front, I make it e to the j pi over 2, and then I pull it into this thing. So I've got that negative j, or negative j times beta r, and then it's going to be, and the angle is added or subtracted. In this case, it's subtracted. Now when I do that, let me pull it down here. E in the time domain will become, after you do this, it'll have that 10 over r business right there. Then the angular variation times cosine theta. We know that's 60 degrees over the sine of theta right here. And then, this is down here. Then what's going to happen is you're going to have the cosine of omega t minus beta r here, and it would be plus pi over 2 radians. Now I'll tell you, I could fool around this and make it a sine if I wanted to, and this would be in the a theta direction. Now you asked me about this. For Wentworth's book, in this answer, he's going to have a single value here. Y'all follow me? What he'll do is have the 10 over r, which is 2,000, right? And then for this, he would have, well, this is going to be the cosine of 45 degrees, or 1 over the square root of 2, and then it's divided by the sine of 60. Sine of 60 is square root of 3 over 2. And you can see this is really square root of 2 over 3, right? Y'all follow me? Because 2 is 2 to the 1, this is 2 to the 1/2. It's 2 to the 1/2 over 3 to the 1/2, or square root of 2/3. Y'all follow me? Anyway, my point is it's a number, whatever that is. Then he'll have cosine. Now, for the form here, the omega is the coefficient of t. Y'all see that? Can y'all follow me on that? He gave us a cosine of 2 pi times 10 to the 9th t. Whatever that the coefficient of t is inside that cosine waveform is omega. Does everybody understand that, class? Okay, I gotta make sure you do, because sometimes there's a disconnect. So I just put in right there, I can put, I'll put omega t there, and I can put the 2 pi times 10 to the 9th t minus beta r. Well, how do we get beta from this, class? I know omega is 2 pi times 10 to the 9. How do I get beta, anybody? What is beta? Is this lossless, class? Yes, right? What is beta in a lossless environment? It's what? Omega times square root of mu epsilon. Do y'all remember that, class? If this is free space, it's omega divided by, what is C? Thank you. So this is really omega, which is 2 pi times 10 to the 9th, right? Over C, which is 3 times 10 to the 8th. So what is that? That's 20 pi over 3, is that right? 20 pi over 3 is beta. So that would be 20 pi over 3 r plus pi over 2. Now here's the crazy part. Some people put that in degrees, but you can't mix degrees and radians, right? So leave it all in radians here. So just leave it as pi over 2. And that would be a theta. The units would be volts per meter. Is that what it has? Now, I don't know what that number is, but anybody check that?
It should be around it.
What's that?
I think it's around what he had. I'll check really quick.
I'm sure that's it, but this number right here is the only thing I don't know, but it's just punching numbers. There's nothing fancy about that. Y'all follow me, class? Now the real trick with this is, from this, you get omega, then you get beta. Y'all with me? And the current value used there for I naught is just this, because that is the current magnitude at the point where it's fed. You got me on that, everyone? How many understand this point? Now, I'll give you the theory behind how you get that in a second, but here's the thing I know from this class. What people are gonna take away, remember, they're gonna remember, hey, that's what it is for an arbitrarily long, and that's what it is for a half-wave. I guarantee you they'll remember those two things, and they'll have that. And you're gonna ask me, do we have to know that we memorize this? I will give you that, and I will give you this. This, right? I'll get rid of that thing and I'll give you the form for a half-wave dipole. Fair enough? Now, don't give that to you for a short dipole. You've got to know it's a sine theta variation. But for a half-wave dipole, arbitrarily long dipole, I don't expect you to memorize it. Fair on that? The other thing is, this is the power density. And that's important that you understand that that is the power density. Good on that, class? Did that answer your question, Ms.?
Yes, thank you.
And I mean, if we had the E field, y'all know how easy it is to get power, right? Just take that E field, square its value, right? So the power would vary as a cosine squared, right? And whatever that is, you square that value, then you would, it's the instantaneous power now. So instantaneous power is a little different than average power because there you would do what? How do you get instantaneous power in a resistor? It's V of t times I of t, right? So it's V of t squared over R, right? The RMS power, or I should say the average power, is V naught squared over 2R, right? Divided by R because you have to get the RMS value of the voltage is squared. Here, what you would do, the instantaneous power would be this right here squared over eta. Y'all hear me? But the average power would still be given by that. Okay. All right. So I jumped ahead of myself, but I think I answered your question. And the class probably really wants to hear that. What do we need to know and how do we apply it? This problem's a little esoteric. I would not give you something where I'm asking for a time. Usually I never ask for time varying forms. Now, any other questions? Good question. Because it led right into the lecture. Go ahead.
Will we ever have an antenna that's not on the z-axis?
Okay, that's a fair question. Possibly. Now here's why. If the antenna was oriented on the x-axis, then what you would have to determine is the angle between whatever the radius vector is and the axis of the antenna. Y'all follow me? Everybody makes the mistake of saying, well, this has got to be on the z-axis to get it right, because everything here is in reference to the antenna orientation. So this angle has to do with how R vector is displaced in its pointing direction from the antenna. It could be on the X or Y axis, or it could be arbitrary. As long as you can tell what this angle is, you got it. Now, the orientation of the fields would also vary, but I'm not trying to confuse you by giving you some kind of crazy proloid spheroid coordinate system or something. I just want to make sure that we're clear that this is the measurement that's important in the magnitude. And the other important thing, obviously, is I that R. Right? Those are the things that dictate the magnitude. The E field's always going to be perpendicular to R. All right? And the way you get it, the component of the E field will be always along the axis of the antenna. The H field, when we have no component, if you look at the H field, it's coming out of the board, isn't it? In the plane there? See how the H field has no projection on the current that caused it? Y'all with me on that, class? In other words, it's perpendicular to the board, it's perpendicular to the E field. If you take the projection of this E field vector in the plane of the board, you see how you get a component here? All right. If you take the projection of the H field, you get no component along the axis of the antenna. This sometimes helps. Got it, class? Right. Yes? Yes?
So if you were to have something like that on the x-axis, would it make the problem easier to like assume that it's the z-axis and just adjust your?
This is one of those questions I don't know how to answer. As long as you can do that, reorient it if you want, but the real thing is making sure the angle to the R vector, wherever that is you can get. Now, almost always you can get it from trig or something like that. But I don't try to confuse you with that. All right? And there's enough to confuse you in this course about that. Okay? All right. Now let me get on my lecture. There we go, in general, why that works, why that happens. This is backwards, but I'm gonna do it. Now, if you ever have rigs for this course, I think he blows through the proof and just puts that up. But I like to talk about the proof.
That's the equation. It's like
I should ask this. Besides you, is anybody else going down for the LSU game? Is this official or unofficial? I mean, are you part of the band or anything like that? All right. I don't know what the weather's going to be like. Be safe. All right. I'm telling you that right now. I don't have any idea what the weather's weird. Some people said a week ago they might even have a hurricane in that area, but they don't, right? So it's clear sailing. I promise you they did. There's a hurricane, supposedly they were thinking about relocating LSU game up here this year. Did you hear that too or not?
I heard that.
Yeah, I mean, that was probably just.
It looks like it dissipated into rain.
It did. But I want to make sure, have a safe trip down there. LSU has always been one of those times when students vanish for a couple of days, and I don't know why. We all know why. I don't want to take that far, but. All right, wow. So now, here comes the theory. You can just put down your pencils. This is and enjoy. I'm going to try to give you discussion. If you can appreciate what I'm about to tell you, it'll help. I really mean this too, because you can write all the math down. I'm not going to ask you to solve this way, but I want you to appreciate what goes on. So, in general, we know if we have a short little dipole that has some I on it, and it's dz thick, then if I come out, I'm going to orient it on the z-axis. If I come out some angle theta away, this would be a short dipole, wouldn't it? It would look like a very short dipole in wavelengths. I could say if I'm out at distance r, the E field here, or in this case the differential E field, would be J eta I, or J eta beta, pardon me, times I of Z over 4 pi r e to the minus j beta r. Then it would be a sine of theta in the a theta direction in volts per meter. Now we've gone through that. That's saying if this thing's a short dipole, if it's dz long, and the one thing somebody should have yelled at me about is there's no length in here, so I'm going to put in a little dz right here times the sine of that. Anyway, that's what it is. Do you all agree? It's a short dipole. Instead of L, I put in dz. Now, if you have a long dipole, again, it's centered at the origin of length L, and L is going to be longer than lambda over 10. Then I'm going to use R as the vector, and I'll be consistent with Wentworth's book, that's measured from the origin to the point of observation of the field. So you're out here, and car insurance. They want me to help me pay off my student loan. Something. I don't know how I'm on a no-call list and everything like that, but they still get through. That's what I'm after right there from the total. Here's how I do it. I come up here a distance z away, and now this is going to be the height c, and I assume I have an antenna right here, a little chunk of antenna that's I dz, and it gives rise to an electric field dE up here. Only the distance now is r, and if you look at this distance here, this is theta. This distance difference is simply z times the cosine of theta, right there. So I can say my r prime here is really r minus z cosine of theta. This will make sense in a second. What I'm really trying to do is set up, I'm after E, maybe I'll say it this way. I'm after the total electric field, but what I'm gonna do is get the differential field right here, given by that. And here, for I of z, I'll put in the value here. Instead of r, I'll have r prime. Everything else is the same. And then I'm gonna have to do something where I define the current now, I of z, since it's center fed and long, that's equal to I naught here times the sine of beta L, right, or beta times, the way Whitmer's book does it, it's beta times the quantity z, or I mean, it's L over 2 minus z is the way he does it. L over 2 minus the magnitude of z. This just says that the current along this thing is going to look something like this. It's going to be symmetric about the origin, and if L over 2 was non-existent right there, then it would go to 0 at the center, but usually it's something, for a half-wave dipole, it's a perfect sinusoid. I'm just going to tell you, half-wave dipole, think about it. It would be an exact half sinusoid for the current distribution there, magnitude. Now, the differential electric field will be given by this mess, so it would be J beta over 4 pi. And here we make the case, if you're at a distance r away and we're assuming r is much, much greater than L, then 1 over r is about equal to 1 over r plus or minus L over 2 cosine of theta. In other words, no matter where I am, at the top of the antenna or bottom, when I'm a long way away, that distance r is about the same, so 1 over that distance is about the same. That means I can leave that guy alone. Now, I have this right here, which is I naught times the sine of all that, so it's times the sine of beta times L over 2 minus the magnitude of z as such, and then it's going to be e to the minus j beta, and that's that r prime right there, and that is r minus z cosine of theta as such, and this whole thing's times the sine of theta also in the a theta direction. And here I got to put in the dz. So just trust me on this one. What I've done is taken this, turned it into the differential dz. The current varies as a function of z by a sine, and then that vector r prime is really this. And try to appreciate, I'm just showing you how it's done. Now, to get the total E field, you got to do this. Y'all follow me? Here's the integral in his book. He doesn't really give straight up. He says it's kind of like this, but it's really not. Y'all see there's a whole bunch of constants, right? Here's 2 tricks to this one. Usually in grad school and stuff in the senior course, you'd be asked to prove this. There's 2 tricks to this. The first is this term can be broken down as e to the minus j beta r times e to the plus j beta z cosine of theta. Y'all follow me on that? That's the first thing. And then it results in this integration. E itself, all the constants I take out in front, would be j eta beta here over 4 pi r here. The e to the minus j beta r comes out in front, right there.
Would the I naught come too?
Yeah, I naught, right there. And then I'm left with this. I got the sine of beta times L over 2 minus magnitude of z here. I've got e to the plus j beta times z cosine of theta there. I have a sine theta term, but this won't matter right here. Sine theta times dz would be in the a phi direction, and it's from minus L over 2 to L over 2. Y'all see this right here? Now I want to tell you something. You look at that, the integration is with respect to z, right? I can take that sine business right here, out front. But here's the trick. The truth is you've got an e to the some constant z. It's like an e to the az. Do y'all follow me? And you can take this sine. You can first make it using the half angle formula, sine A minus B. You can break it up that way. Then you're left with some sines and cosines, and you can use Euler's identity on each. Now it's a little nerve-wracking doing this. Then you put that in there and you group all the coefficients of the exponential and break them off as e to the something z and integrate term by term, and then you have to kind of massage it and get it into a closed form. Now it's an irritating thing. I'm just going to tell you, you have to do this at least once in your life to appreciate it. All right? And then you'll see through some clever ways to do it. But he doesn't bother with it in his book. He just says, after all is said and done, you get what I put on the board last time. Earlier today. You get E is equal to J60 after everything's done over R times I naught. A lot of times they do this. They group E to the minus J beta R over R. That's a phase and a magnitude. They'll group that together. Then they'll put the angular form next to it after that. Then it varies as that cosine of cosine of beta L over 2 times cosine of theta minus the cosine of beta L over 2 all over the sine of theta in the a theta direction. You can get that doing this integration. I'll say one more thing just in case anybody here is feeling frisky and wants to do it. See how magnitude is z? You break it up in integral from minus L over 2 to 0, where this, since it's going to be negative, right? Then you put a positive there for that part. And then you break it down for the second half from 0 to L over 2, you just leave it minus z. And you have to break it into two parts. It takes some time to do, but it comes out to this, I promise you. It's an irritating thing, and trust me on this. Something I gotta say about this. Remember how I called that small f of theta? And you remember how the square of that was capital F of theta, right? Now, here's some things that are important. That's the E field. I gave you the power density earlier. If you were to calculate the maximum gain, this is in his book. But remember, for the power, I'll put it up here again. The average power density for an arbitrarily long antenna was equal to 15 over pi times I naught squared over R squared. And then it was times f of theta, where f of theta was my small f of theta squared, or it was that business I put up there a second ago. Y'all follow me? That's what that is. I'm just trying to say, I put that up there before, right? Now, when you look at P normalized as a function of theta, what does normalized power mean? Normalized power density? In your own words, guys? Say it again. Somebody say something.
It's like you said magnitude of 1, right?
It has to have a magnitude maximum of 1, right? Do y'all remember this? So what you would do is literally take this equation. You get rid of the r's. You can set r equal to 1. Get rid of everything in front of there. It's only going to be a function of that. Now here's the thing. You see this, it's really would be what? F of theta over the max value, right? Maximum of f of theta. Y'all follow me? Before, when we had the sine squared variation, that had a peak value of 1. It was normalized, right? If it was cosine squared, it's just cosine squared. But this thing right here, it can have a peak value much greater than 1. You hear me on that? So what you have to do is take f theta over f max. You have to find the maximum of that. All right, now, I can get into this with, but I don't really want to. How do you always find a maximum of a function if it's a function of angle, say, or a function of x? How do you find the maximum of f of x, anyway? There's one trick all engineers know. You take the derivative and set it equal to 0, right? Because where the derivative is 0, it's either a peak or a min, right? And then you go ahead and take that value and you stick it back into the original equation, and you see if it's the biggest or smallest. Do y'all remember this, class? That's the way you do it for this. To explore where the maximum is of that, you have to take the derivative of the, you don't have to do it this way, you can do it numerically. Most of the time, you just plot it and you'll see. All right, plot it's the easy way. But technically, you take the derivative of this, set it equal to 0, find the roots of that, then take those values and evaluate that function to see where that function was the maximum. Whatever that maximum value is, you use here. Now, the reason I said that is because if you want to get B max for this, he does a lot of this in his book. The maximum value of the directivity technically is 4 pi over the integral from 0 to 2 pi over the integral from 0 to pi of P normalized as a function of theta times a solid angle, which is sine theta d theta d phi. Y'all remember this from the quiz? All right, now, I would never ask you to do something this crazy on a quiz or test. However, for homework, Wentworth's big on asking people to do that, all right? I may give you an extra credit assignment where you can gather some points for your quiz grade, to support your quiz grade if you had a bummer one time. I'll drop the lowest, but a few people have had more than one bad time. And, but I'll ask you to do something like this. You got me on this, class? I'm just trying to set the stage for it. Now, it's not that bad, but I can come up with a situation you won't find Google. Right? You're going to actually have to use MATLAB and go through it, all right? But it's not that bad. Y'all know that I'm just trying to do my job here to get you involved at some level so you can appreciate this stuff. I don't like making your life hard, but you should at least understand that's the goal of this. Now, so without going through the whole 9 yards, that's sort of what happened. Now, something I got to tell you about these dipole antennas, and I'll get into monopoles in a second. There's one thing that comes out of the half-wave dipole that's real important. And I don't want to worry too much about the arbitrarily long antenna other than the patterns and the maximum directivity. Because for arbitrarily long antennas, you get some weird power patterns. You can have things that are clovers the way they look, and I'll show you what I mean. You can have power patterns that have all sorts of peaks and troughs, depending on the length of the antenna. Usually with antennas, usually. For straight wire antennas, I'd say 95% are half-wave dipoles, or they're a little less than a half-wave dipole, and I'll explain why in a second. But there's usually not just one of them, they're in an array. So, when we talk about dipole antennas, and now I'm going to say specifically half-wave dipole antennas. So here, I've got an antenna. It's centered at the origin. Its length is lambda over 2. It has some feed current here, I naught. I'm out a distance r away, and here's the angle theta. I gave you the electric field and power density from this. That was J60 over R, e to the minus J beta R over R, times my f of theta that I've put on before. All right? It'll be the A theta direction. And I gave you the actual value of the average power density, which is going to be 15 over pi r squared, I naught squared, times capital F of theta in the AR direction. Are you with me on this, class? I've put those up there several times if you want to know what f of theta is, this is again for a half-wave dipole. F of theta is just cosine of pi over 2 cosine of theta over the sine of theta. That's it. And then capital F of theta is just the magnitude of small f of theta squared. That's it.
Are there supposed to be two R's, or did I write it wrong down? Okay, cool.
You wrote it right. Actually, let me put an R under there. I don't mean to hurry on this one, but y'all with me on this? I put them up earlier sometimes, right? Yeah.
Isn't it also a function of the currents?
Yeah. You are right about that. Absolutely. That's on me. Okay. All right. Those two, E field, power density, important. There's one other thing that's real important. It's the radiation resistance. Don't worry about the calculation. Write this down. For in exact L equals lambda over 2 dipole, the radiation resistance, or the input, or the actual impedance, let me put it that way. Call it Z, the antenna, the input impedance. This is the exact impedance. Would be 73.2 plus J 42.5 ohms. Now that's the total antenna impedance. If you make it exactly a half wavelength, that's what you should get. Here's the truth about that. The antenna impedance is also a function of the thickness of the wire. If you get a wire and the circumference of that wire is approaching like 1/10 of a wavelength, this starts changing fairly rapidly. I'm being honest with you. Another thing that happens is this. Most of the time in the real world, they do not use an exact half-wave dipole. What they'll do is trim down the length just a little bit. And here's why. Because if the antenna is L equal to about 0.485 lambda, just a little bit less than 0.5 lambda, then your Z antenna is strict real. It's just about 73 ohms, and this imaginary part goes away. The reason you want that is it takes less voltage to keep the amount of current. Y'all follow me? So that's real important. Give me one more second. That's real important. Now for this antenna, remember this. This antenna is used all the time. The E field and the power are the same. E and P amp are the same as if it was a half-wave dipole. So you don't lose anything in terms of power or E field or H field for that matter. Y'all follow me? Now, the maximum directivity for all of these, the exact and this antenna, this slightly shorter antenna, D max for this, without me calculating it, but you know how to calculate, is 1.64. It's just a little bit better than a half. Remember, I mean for a short dipole was what, 1.5, right? 1.64, just a little bit better. You want to know something else? That cosine of pi over 2, cosine theta over sine, it's almost the same as a sine of theta. Not quite. So if you were to plot in polar coordinates the actual normalized power density for a short dipole, you'll get this. And it will go out to 3/2, or 1.5. If you were to do the same exact plot for a half-wave dipole, it would look like this. It's almost the same. Basically, the lambda over 2 dipole would have a peak value of 1.64. This one has a peak value of 1.5, and they're almost overlaid. The big difference, hear me now, the big difference of that half-wave dipole is this right here, 73 ohms. Because for a short dipole, do you remember how it could be of the order of less than an ohm and more, or less a lot less. So it takes a whole lot more current to get the same amount of power radiated, and that's a big, big deal. You don't want much current. Y'all good with that? All right. So on Friday, I will give you a short quiz that has to do with dipole antennas. Half-wave dipole antennas based on the home. I can't be any more clear, all right? Please come prepared for that. I'm not gonna ask you to prove something. Yeah. Did you have a question? Are you gonna be here for that or not?
I'll stick around for it.
All right.
I'll be here.
I'll
Would you, I
stick.
mean, drive safely on the way down here.